Okay, so hi everyone, this is the week 5 tutorial for this course, uh, Thermal Physics. And in this course, this week's lecture is mostly based on the specific heat topic. Okay, so mostly specific heat. There are mainly two main theories of specific heat. One is the initial theory, that is the Einstein's theory of specific heat, and the second one is the revised version of that is the device theory of specific heat, right? And also the classical part of the specific heat idea is the Dulong-Petit's law, that is also the part of that total lecture. And apart from that, there is also questions from behavior of real gases, where in kinetic theory you have studied about ideal gases. Now you have questions, and you have the you have information about the behavior of real gases and how they differ from ideal gases, and something related to that, but mostly it is based on maximum problems are given from the specific heat context only. So first of all, I'll solve previous assignment. Okay, and I think most of the questions in that assignment is actually common to the assignment that is given to you in this term. So basically most of the questions you will find common, and then some few questions which are a bit different from whatever we will discuss initially. I will also cover that part, so that you have also a fairly good enough idea of how to attempt or approach those problems in the assignment as well. Okay, so let us take our calculator and etc., because this will be a numerical sort of a problem most of the times. So I will solve side by side. Okay, so let us ignore this part because this is the current assignment that you have. All of this I will not solve rigorously, because as I said, most of the problems that I will be solving here is from previous assignment of similar type problems. Okay, right? Yeah, so basically we'll read the question one by one and then solve it. Okay, so the first question is, let us read this. The Debye temperature for carbon crystallized as diamond is 2230 Kelvin. Then calculate the heat capacity for diamond at 30 Kelvin. So basically you have the Debye temperature mentioned. You have to calculate what is the heat capacity CV of diamond at some other temperature T equal to 30 Kelvin. Okay, so as you can see that the question is based on the Debye's theory of specific heat, because it has particularly mentioned the Debye temperature for that particular sample. So any crystalline solid or any sample that you deal with will have a particular Debye temperature characteristic to it, right? So based on this, in the question it is given that theta d, let's say we identified this as our Debye temperature. So Debye temperature theta d is mentioned for carbon diamond form is equal to 2230 Kelvin, right? And you have to calculate what is the specific heat. We say specific heat at constant volume. So this is the specific heat at constant volume. And you have another information that you are given a T of 30 Kelvin, and this at this T, what's CV at T equal to 30 Kelvin for this sample, when you are given this information of theta d as this. Okay, so basically as I said that because this question explicitly mentions the Debye temperature, so it will be using Debye's theory of specific heat, which is basically not independent only Debye's theory. Basically it is combined theory of Einstein and Debye. So because Einstein initiated the theory, he used the quantum aspect to the problem, and therefore he gave almost a qualitative match of behavior with the experimentally seen trend. And then Debye actually improved the theory much more, started from where Einstein's theory was lacking, and then it resembled even more with the real experimental behavior of samples. But we will call it Einstein and Debye theory of specific heat. If you have already probably learned this theory from the lecture videos or this week's lecture content itself, so without going into further details and delaying this, we'll straightforward use the formula that from this theory there is a specific heat formula given. Okay, and remember that there are basically that formula actually contains an integration which needs to be numerically solved. So you can only take out a simplified solution if you mention the temperature limit you are working in. Like for our case, because we have to calculate what is the CV at T equal to 30 Kelvin, and 30 Kelvin is a significantly low temperature, right? So we can take the approximation of low temperature limit for this problem, and therefore we can get a simplified closed formula of the CV from this Debye-Einstein theory or Einstein-Debye theory, whatever. So basically this is important, that this we consider, this is taken under low temperature limit approximation. Okay, and using this idea that if you have the low temperature limit form, then you will have a straightforward, very straightforward and actually closed box format formula for the CV, which is 12 pi to the power 4 by 5 times Na, which is the Avogadro number, into Kb Boltzmann constant, into T by theta d whole squared. Okay, so this is your specific heat or heat capacity at constant volume CV, and this is the formula which involves only two parameters, values that we have to know explicitly, that is that current temperature T, which is in our case 30 Kelvin, at which we need to calculate the CV, and the other thing is the Debye temperature theta d, which is also mentioned in the problem itself. Okay, so basically we'll now directly substitute the values and get what we and see what we get as an answer. So basically this is equal to 12 pi to the power 4 by 5 into, so basically you already know that Kb times Na is nothing but R, where R is your universal gas constant, right? Universal gas constant. So you directly use that value, and if you want to calculate this in SI, then you know that R's value in SI is 8.314 joule per mole Kelvin. Okay, so this is equal to R, which is equal to 8.314. in SI value we mention everything. Okay, so just remember we are taking the SI unit here, and this into T by theta d whole squared. So basically T is 30 Kelvin and theta d is 2230 Kelvin, this thing whole squared. Okay, so 0 and this 0 cancels out, and this is equal to, if you use your calculator, so this, do this carefully, that 3 by 223 whole squared into 8.314 into 12 by 5 into pi to the power of 4. So sorry, I made a major mistake. That's why the formula is not giving us the correct answer, because here there is no square but there will be a cube. Sorry, so there will be a cube sign. Please rectify this. There is a cube sign, not square. I by mistake put it as square earlier, but this is a cube term. Okay, so if you now do the calculation carefully, so this is 3 by 223 whole cube into 12 into pi to the power 4 divided by 5 into 8.314. So we are getting this equal to 4.73 into, so let us check what was the answer that is given, right? So 4.73 into, where is the answer? Yeah, 4.73 into 10 to the power minus 3. That is what we are getting. So this is matching with one of the options. So basically I was just checking that whether that option is present or not. So this is 4.73 into 10 to the power minus 3. And because we are calculating in SI unit, so basically the unit of this R will count here. So joule per mole Kelvin. Okay. So this is your answer, that this is your CV at constant volume. So here this is like D, 4.73 10 to the power minus 3 joule per mole Kelvin. Accepted answer is also D. Okay, so then moving on to the next question, that for copper Debye temperature is given as, Debye frequency is given as 2.49 10 to the power 12 Hz. Then calculate the Debye temperature for copper, where 4 options are given. So first of all, this is a very straightforward problem because this does not only concern the specific heat aspect, but this is true for any temperature scale and energy scale we associate this formula with. So this is well known that if let's say at some temperature T, the thermal energy will be like something like kV into T, right? So where kV is a Boltzmann constant. But if yeah, so but if there is a frequency also mentioned, so from the frequency we can calculate the equivalent energy, which is like E equal to h nu, and then we equate that energy with the thermal energy which is coming from kBT. So basically for copper it was, right? So copper is a metal, obviously copper is a metal. So and it is mentioned that the Debye frequency nu d is the Debye frequency (2.49 into 10 to the power, I think 12 or 13, what was that? 10 to the power 12, 10 to the power 12 Hz. Okay, so basically the idea is that you have to equate the energy scales. So the energy you get from the Debye frequency of vibration is like h nu d is equal to the energy coming from the thermal energy at kBT. So this is equal to kBT. But here okay, so okay, so we are discussing problem number 2, which is about the what is you have to calculate the Debye temperature when you have the information about the Debye frequency of copper, right? Now you know that in this type of problems you always have to find for equivalent energy scales, right? So in our case, equivalent energy scale is very basic because already we have the information about the frequency. So all you have to do is that you have to equate the thermal energy which is related to the temperature with the energy corresponding to that frequency that is mentioned to us. Okay, so basically we know that energy dimension E. So if E is energy, then we know that E is normally h nu, right? Then this is the energy for corresponding to any wave or any pulse that has a frequency nu, right? Then thermal energy, okay, thermal energy, let us call it E subscript T, that is always Boltzmann constant times the temperature, because this is coming from the temperature, so this is the thermal energy. Okay, so in this case, in that material, whenever we are comparing these two energy scales, so these two should be equal, right? Then only you will get the temperature information from that frequency information. So this is very basic, that if nu is equal to nu d, that is the Debye frequency, then at that point the temperature will be, that is equivalent to that frequency, will obviously be the Debye temperature. So here T is also equal to Td. Sometimes we also write the Debye temperature as theta d. So whatever notation you choose to do, but the idea is that your Td is just H times nu d by Kb. So now you put the values of the different terms carefully, that your Planck's constant is 6.626 into 10 to the power minus 34. This is in SI unit. So your frequency nu d, which is mentioned in the question, is also in 2.49 into 10 to the power 12 in Hertz unit, right? Then Kb is also, you have to take the value of Boltzmann constant in SI, so 1.38 into 10 to the power of minus 23. Now just use your calculator and you will get a value of 119.6 Kelvin. So let us see what answer option is matching with this answer. So right, in our first question the answer was, sorry, this is the current assignment. So first we will solve this assignment and then we will move on to that. So question number 2 is about 119.6, which is the accepted answer, B, right? So this is done. Then question number 3 is about the specific heat C of copper at very low temperature is found to depend on the absolute temperature T according to the relation C equal to AT cube in SI unit, okay, where A is a constant. Then how much heat must be added to the system to raise the temperature of 10 gram of the material from 10 Kelvin to 20 Kelvin. Now if you read the question again and carefully, you will find that you have the material given as copper, and you have the information about the mass of the copper, which we have to deal with is the 10 gram mass, right? So mass is given. Then you have the information that you have to change the temperature or raise the temperature from a lower value, which is T1 10 Kelvin, to a higher value, which is T2 20 Kelvin. And the temperature dependence of the specific heat for copper in this case, which is given as C equal to AT cube. This is a relation how specific heat is dependent on temperature, and it is explicitly mentioned in the question, so that you don't have to use a formula on your own. They have just mentioned you the formula, and A is an unknown constant in the problem, so keep A as it is, because in the option answer also you see that everywhere A is present, so you don't have to bother about the value of A, you just keep A as a constant in the answer itself, okay. Then another thing is that it is mentioned that where is that? Yeah, absolute low temperature. So copper, specific heat of copper at very low temperature is found to be of this formula. So this is also important, because you know from the Einstein and Debye theory of specific heat relations that the specific heat does not behave monotonically in all the temperatures, right? So it has different kind of behavior in different temperature zones. Especially in the high temperature range, it behaves almost like a classical what do I say, classical nature of Dulong-Petit's law, that it gets saturated and constant for a solid at a value of 3 into R, right? And then as you lower the temperature, it deviates from that constant value, and it has a temperature dependence, that it falls off as the temperature decreases, and it reaches it as the temperature tends to absolute zero, C also tends to 0. That is a specific heat nature, and it is also experimentally found out for different materials, and also theoretically verified by the famous Einstein-Debye theory, that at low temperature, when the specific heat decreases as the temperature decreases, so as per Einstein, it used to follow an exponential decay with temperature, but later on it was like improved and more more consistent with the experimental findings that was done by Debye, that he modified the formula a bit, and therefore at low temperature it was not falling exponentially with temperature, but it had a T cube dependence, that C is proportional to T cube, which is basically coming from the phononic contribution, of course, and then it was decreasing as the temperature decreasing. So I can almost think of it like this, okay. So maybe this is not very accurate in terms of a diagram, but I am just trying to roughly draw it how it should behave. Okay, so it is not absolute. Do not take it scale wise, and neither should you take it absolute for all materials, because different materials has different sort of a behavior. But this is the most general kind of a thing, that at high temperature, this is high temperature limit. All I am trying to say is that for different temperature limit, the specific heat behavior should be different. So in the high temperature limit, Ct is equal to 3 times R, okay, which is equal to constant for solids, and this is from the classical Dulong-Petit's law. So basically it comes from the classical idea of equipartition of energy, and it was given by Dulong and Petit. So it is classical Dulong-Petit's law. Later on also in Einstein's and Debye formula with quantum considerations, quantum like approximations, there also in the high temperature limit it matched with the classical one. Okay, and then according to the classical one, it should have been constant throughout all the temperature, but actually in experiments it is found that it decreases with temperature. So as you decrease the temperature, you will see that especially at low temperature limit, okay, then Ct is proportional to Tq. This is the low temperature limit, and the in between temperature, you don't have an explicit closed form for that. It's just decreases with temperature, but the exact form to get that, you have to basically numerically integrate or solve a particular relation of C and T, connecting C and T. That is given in the Debye formula, Debye theory. Okay, so that we don't bother about. Mostly we'll deal with high temperature either or the low temperature range, right? So in our question, they have mentioned that we are dealing with the low temperature range of specific heat, and of course that is true, because they have mentioned the temperature values they have given is just 10 Kelvin and 20 Kelvin, which is of course a low temperature. So we'll be dealing with only this part, which they have already mentioned that it has a C equal to A times T cube dependence, which is basically the phononic contribution of specific heat. That we will not get into, but the idea is that now let us try to solve the problem that you have specific heat Ct is equal to A times T cube at low temperature limit, right, where your A is a constant that we don't know the value of, and we don't try to get the value of. Okay, and the material is, I think, copper, right? So copper, and the mass is given as 10 gram, which if you convert in SI, so it is just 10 into 10 to the power minus 3 kg, right? And it is said that the temperature you have to change from T equal to 10 Kelvin, which is T1, to T2 is equal to 20 Kelvin, which is T2. So increase the temperature from T1 to T2 such that T2 is greater than T1. So in this process, how much heat has to be absorbed for that material under these conditions to raise the temperature from 10 Kelvin to 20 Kelvin. So probably you are familiar with the basic expression of heat absorbed relating with specific heat, that your dq amount of heat is equal to m times C times dt. It basically means that because you know that specific heat Cv or Cp whatever is nothing but the general idea is that dq by dt, right? Now it can be at constant volume or constant pressure depending on whether you are dealing with Cv or Cp. Okay, V or P is constant, then it will be Cv or Cp, but the basic idea remains the same, that it is dq by dt. That means that for unit change in temperature, that when dt is equal to 1, whatever the value of dq is, that will be the value of your C. That means for unit change in temperature, whatever heat will be needed, that much value will be equal to your specific heat, right? So basically this means that now this is mostly for 1 mole or whatever. So in more general sense, if you have to include the mass expression also, then you also have to include the mass term in here. So mostly this molar, these are mainly dealt with molar specific heat. So there is no mention about mass, because this is already taken for 1 mole. But for general idea, when you have to consider the mass explicitly, there you have to take dq equal to mc dt, which is like the amount of the small amount of heat, because whenever we use the term d in front of a term, we generally mean a small deviation or a small change of that quantity, right? So dq is nothing but a small amount of heat. dq is needed to be absorbed or sometimes emitted also, depending on whether you are trying to increase the temperature or decrease the temperature. So I am writing the other option in bracket. So either absorbed or emitted for m mass of a material with C specific heat. So this specific heat is not molar specific heat, this is not per mole, but this is per unit mass basically. So with C specific heat to either increase, or the other option in the bracket will be decrease, because this bracketed terms correspond to this. So whenever you are absorbing heat, you are increasing the temperature, but whenever you are emitting that heat, you are basically decreasing the temperature. So the definition will be how much it will be needed with C specific heat to increase or decrease dt small amount of temperature of the system. Now in our case, they have particularly mentioned that we have to increase the temperature, so dt is positive here. So dq will also be positive, that means you have to absorb the heat to increase the temperature. Now if dq is this, then the total amount of heat that will be needed for any temperature increase will be just an integration over q from one state to the second state, right? So m and c are constant, so only thing that will change from state 1 to state 2 is the temperature. So it is T1 to T2 variation. So if you take the integration, c, m and c will be outside integral and dt will be integrated from limit of T1 to T2, right? So then once you know this, you just use that in here using our information that for copper m was given as 10 gram, which is 10 to the power of minus 2 kg, right? So just put this expression as 10 to the power minus 2. Now in here we have taken C outside integral because we are assuming that C was independent of temperature. That it will be if we consider the Dulong-Petit's classical idea that it is constant and independent of temperature. But by the quantum theory, by implementing the quantum theory in specific heat, you already know that is a more valid theory to correspond to the experimental findings, and that C has a temperature dependence. So C is a temperature function of temperature. So this C cannot be outside the integral when the integral is itself over temperature. So that has to be inside the integral, right? So that we modify that our this thing will be inside integral, and Ct value is given in the question as A times T cube, and the rest of the term will follow dt integrated from T1 to T2. Now you know the value of T1 and T2 from the question, that T1 is 10 Kelvin and T2 is 20 Kelvin. So now A is a constant, so it is obviously coming outside the integral. So it is 10 to the power minus 2 into A into this integral over T cube will be T to the power 4 by 4, and this is going from 10 Kelvin to 20 Kelvin, right? Right. So this is A into 10 to the power minus 2 by 4 into 20 to the power 4 minus 10 to the power 4. Now just calculate it and you will get a value of 375 into A, because this A is a constant, so it will remain in the final answer as well. So this is our answer. Now let us match whether it matches with the option. Okay, so the answer will be option number A. 375A is the answer. Okay, then question number 3 is also done. Then let us move on to question number 4. Now it is asking that for 2 gram of oxygen molecule following van der Waals equation, calculate the pressure at which its volume should be 500 cc at temperature of 27 degrees centigrade. The values of the constants for 1 mole of oxygen are given as B value is given and A value is given, and universal gas constant R value is given. So as you can identify from the question, that this is not a question about specific heat, but it is a question about the behavior of real gases chapter, and therefore it is talking about the van der Waals equation that is valid for real gases. Okay, so basically you have to use the van der Waals gas equation, and you probably already know the formula. So I'll directly write down the formula for van der Waals equation for real gases. Okay, now one things that you need to take as an information from this question is the mass of the oxygen M, that the information that you have to use the van der Waals gas equation. You have to find out what is the pressure, then the volume is mentioned as 500 cc and the temperature is mentioned that you can convert into Kelvin, and the values of the constants for 1 mole of oxygen, that for 1 mole the co-volume value B and the other constant, that is correction to the pressure term A, is given in all in at this is in centimeter, so centimeter unit, this is also centimeter cube. So probably you have to use the whole thing in CGS so that there is no conflict in the units, most of the units. So we will prefer to use centimeter cube mostly for all of them, and the R value is also given, which is the universal gas constant value, right? Now let us go to the blank page and write down the needed equation to solve this. So this is our question number 4, and we have been given oxygen gas, which is O2 molecule. The gas molecule is O2, which is a diatomic molecule because it has 2 oxygen atoms, right? 2 oxygen atoms. Now the mass of that oxygen gas is given as 2 gram. This is in CGS, so we keep it in CGS. We do not convert it because ultimately we need to match all the units, right? Now the temperature is given as 27 degrees centigrade, which is like 27 plus 273, which is like 300 Kelvin. Alright, now it is mentioned that the co-volume B is equal to 32 cc or centimeter cube, and the pressure correction term is A equal to 13.6 into 10 to the power minus 5 atmosphere centimeter to the power 4. These two are for 1 mole, and the volume is given as 500 cc or 500 centimeter cube, which is again in CGS. Okay. Now universal gas constant R value is given as 0.0821 liter atmosphere per mole Kelvin. So just be careful that all the units are in same page, like here atmosphere, so atmosphere it is in same unit. Okay, mole is, there is nothing you can do about mole. Kelvin is also absolute. The only thing you need to change here is about the expression of volume, which is given in units of liter here, but all the other terms are in centimeter cube or cc. So what we'll do is that we'll convert this liter into cc also, so that all the units are in the same type. So you know that 1 liter is equal to 1 decimeter cube, which is nothing but 10 cube, because 1 decimeter equal to 10 centimeters. So 1 decimeter cube is 10 cube centimeter cube or 1000 cc. So this is just 0.0821 into 10 to the power 3 cc atmosphere per mole Kelvin. So the pressure is given in terms of atmosphere, so that we need to calculate from here. Okay. Now the information is already there in the question that you need to use the van der Waals equation for real gases. Anyways, because otherwise you will not anywhere find the constants A and B. These are only present in van der Waals equation. So we write down the van der Waals gas equation for real gases, which is P plus N square A by V square V minus NB equal to nRT. So let us box this equation so that it is highlighted. Here remember that your N is the number of moles of that system. Now if you deal with only 1 mole, then it will be simply p plus n square a by p plus a square a by v square into v minus b equal to RT. Okay, but here for n mole it will be in RT and the n terms will also be inside. And you know that for ideal gas, if you remember that the gas equation there was PV equal to nRT if you are talking about n mole of ideal gas. But this is for real gas, behavior of real gas. So there are some corrections corresponding to that, because real gases do not actually behave like the ideal mannered ideal gases behave as. So this is for n mole, and the right hand side is the same, but there is a correction term in the volume and also the pressure. So this n times v is the correction term in volume, and n square a by v square is the correction term in pressure. These two come because the pressure term, this modification is because the gas molecules in real gas are not inert. That means they interact with each other, where in the ideal gas kinetic theory the one of the main assumptions was that the gas molecules do not interact with each other, right? But they do interact with each other, and considering that and taking that into account, you get a modification and correction term in P. Similarly, for volume also there is a correction term in volume, which is n times B, where the volume is actually basically getting decreased from what it should have been in the ideal gas case. That is because in the ideal gas you also assume ideally that the gas molecules are like point masses, and they do not occupy any volume in the container. But that is actually not true. However small that those gas molecules are, they do have a finite volume that they occupy, and because of that the one molecule is occupying a certain volume, so the other gas molecules surrounding to that will always have a constant to freely move around in the volume of the container, because they will try to avoid the volume that is occupied by another gas molecule, right? So that will actually eventually modify your volume in that equation and basically decrease it from the ideal gas case, because then you have to also include the finite size effect of the gas molecules. So this is the van der Waals gas equation for real gases. And now we can determine the pressure easily, because we have to just derive step by step that your pressure is equal to then nRT by V minus NB minus n squared A by V squared. Okay, so just give me a second. Right. So then if this is the case, then you have the n value. So the n value you have to probably determine, because for oxygen the mass was given as 2 gram. So the mass was given as 2 gram for oxygen. So then you know that 1 mole of oxygen is equal to 32 grams of oxygen. Okay. So then for 2 gram, how much will be the mole? So 32 gram is equivalent to 1 mole. Then 2 gram is just 1 by 32 into 2, which is like 1 by 16 mole. So your n is equal to 1 by 16, right? So then you just substitute all the other terms in that expression, and you have R as 0.0821 into 10 cube into T value is just 300 Kelvin, and the n is just 1 by 16 divided by V is 500 centimeter cube, so we keep that in centimeter cube, 500 minus n 1 by 16 times B is just given as 32 cc, right? So this is 32 minus 1 by 16 square, which is n squared, into A is just 13.6 into 10 to the power minus 5. So this is, so just keep this aside. So 13.6 into 10 to the power minus 5. Okay, so divided by V square is 500 whole square. So this is just, if you take your calculator and calculate carefully, you will get that this is equal to almost 3.09 atmosphere. So this is our answer of pressure. Pressure value is almost close to 3.09 atmosphere. Now let us go back and see what answer is matching with our answer. So 3.09 is in the option and D is the correct answer. Okay, so this is option number D. Right, question number 4 is also done. Then let us move on to question number 5. It is saying that for helium gas, the value is mentioned as 23.4 cc per mole. Given the Avogadro number Na, which is equal to this, then calculate the diameter of helium atom. So your co-volume value B is given and the unit is cc per mole. This is per mole consideration always. Okay, and the volume term is in terms of centimeter cube. Avogadro number you already know. Then calculate the diameter of helium atom. Now this question is interesting because as I was telling you that in van der Waals gas equation, where you deal with real gases which deviate from the ideal gas behavior that we had learnt about in kinetic theory, so it will also deviate from the ideal gas equation, and therefore comes the modified van der Waals gas equation which is applicable for real gases. And there the B term comes from the correction of volume because of the finite size of the gas molecules, right? So basically you can get the idea that this B term has some inherent relation to the connection or some connecting formula to the volume of the gas molecules or gas atoms, right? So therefore we will use that relation to get the relation between B and the volume of that helium atom, and from that volume we can easily get the radius and the diameter of the helium atom. So this is the whole idea. Let me now solve this. Question number 5. So for helium it is a monoatomic gas. That means one molecule has a single atom. Okay. Now your B is equal to your B is equal to 23.4 cc per 1 mole, and your Na is just 6.023 into 10 to the power of 23. Okay, and you need to calculate what is the diameter of helium atom, which is nothing but 2 times the radius. Okay, now as I was saying that B is equal to co-volume, which is a correction or modification to volume term, correction volume term from ideal gas equation to the van der Waals, in short we write as VDW gas equation, for taking into consideration the finite size and volume of the gas molecules, right? So like if this is your one atom and this has a radius of r which is sigma by 2, so then this is the diameter sigma, and this r is equal to sigma by 2 in here. So this is inner part that I have dashed line in. Okay, that part is basically the gas molecule of diameter sigma, and then around that molecule you can consider a sphere of influence. It is basically same as the collision cross-sectional consideration, because any gas molecule that is coming in the range in between that 0 to sigma center to this circumferential distance of around this gas molecule, anywhere they will come, they will collide with this particular molecule that is in yellow dashed line circle, right? So this is the sphere of influence of this molecule, and the sphere of influence has radius of sigma by 2 and diameter of sigma. Now, without making it too much rigorous, I will just directly write down that there is a formula that is there established for the co-volume, that is a correction term B, and the volume of the gas molecules. So the formula is that B is equal to 4 times the volume of a single gas molecule. So then B is equal to just 4 times, because we consider these gas molecules as sphere, assume in spherical shape, because that is the simplest idea. And the radius is just sigma by 2 equal to r. So this is 4 times. Now the volume of the gas molecule is the volume of the sphere of radius sigma by 2. So the volume of the sphere is then 4/3 pi r cube, where r is sigma by 2. So sigma by 2 whole cube will be equal to 4 into 4 pi by 3 into sigma cube by 8. So this is just 2/3 pi sigma cube, right? Now this is for a single gas molecule. But in the question, if you see it correctly, you have information about the Cc, unit was Cc per mole. That means this is the B value per mole of the gas, right? So you have to consider 1 mole of quantity. So even if this B is equal to 4 times the volume of a single molecule, this is for a single molecule. So for 1 mole of helium, which is equal to Na, Avogadro number of molecules of helium, for that the B value will just be simply multiplied by Na. So this is 2/3 pi Na sigma cube. Okay. So this is just like sigma cube will be then 3b by 2 pi Na. But sigma is equal to 3b by 2 pi Na to the power 1/3. So this is just 3 into B is 23.4. This is Cc per mole divided by 2 pi into the Avogadro's number is 6.023 into 10 to the power 23 per mole. So this per mole and per mole cancels out, and 1/3 power. So you are only left with Cc, which is centimeter cube, to the power 1/3 is just centimeter. So you are only left with, if you calculate this carefully, we will get that this value is 2.64 into 10 to the power of minus 8 centimeter cube to the power 1/3 is centimeter, and this is just 2.64 into 10 to the power minus 10 this is meter, because this was a centimeter. So if you have to calculate in meter, then this is just 10 to the power 2 multiplied 10 to the power minus 2. So this is 10 to the power minus 10 meter, which is nothing but 10 to the power 2.64 angstrom, because 1 angstrom is equal to 10 to the power of minus 10 meter. So this is 2.64 angstrom, your answer. So let us match what option does it match with. So question number 5 is 2.64 or almost 2.65. So our right written accepted answer is C. So this is also solved, right? Now so rest of the 5 questions. Okay, then question number 5 is about question number 5 we have done. So question number 6 is about the ratio of RTC by PCVC for an ideal gas. We have to get the value, right? So this we already know from our earlier knowledge that for ideal gas the RT by PV ratio is always 1. So even if you take the critical constant critical values, that is TC, VC and PC, it is still 1. Now because for ideal gas you know that, let me get a blank page and explain that this is question number 6, right? Yeah. So for ideal gas you know that the ideal gas equation is just PV equal to RT for N equal to 1 mole of gas, right? Where R is the universal gas constant. Now here, from here you see that RT by PV is just 1, right? It's 1. Right, so then just give me a moment. Yeah. So then RT by PV is equal to 1. So even if you put the value of T, P and V as TC, PC and VC, that is also 1. Okay, so this is the deal for ideal gas. Now this idea of critical parameters like critical constants of temperature, pressure and volume is mainly important for the real gases, because there you have a value of RT by RTC by VC which is deviated from 1, and from that actually you can get how much is the deviation of the gas from a real ideal gas behavior, from an ideal gas behavior. Basically because real gases or practical cases, the gases do not behave exactly like the ideal gases that we have learned about. So their RTC by PCVC ratio is actually called, I think, the critical coefficient, and that critical coefficient value which should be 1 for ideal gas, and it is deviated from 1 for non-ideal or real gases, and that deviation actually tells you that okay, this gas is non-ideal and how much is the deviation from the ideality. So this is the idea. Now for the sake of it, sometimes you have a similar question, like you may need to calculate what is RTC by PCVC for real gases. So in that context I'll also show you that solution so that it will come in use later. And so basically if you take this real gas, so for real gas or non-ideal gas, what is RTC by PCVC? I think this is called eta C, which is equal to critical coefficient, which is not equal to 1. Now the critical point parameters are PC, VC and TC. So basically the idea comes from here that for ideal gas you know that your P versus V diagram for a constant temperature will be like, if this is an ideal gas then this is just like this for different constant temperature. This is T1, let's say T2 and T3. These are isotherms, means constant temperature curves, and this PV curve is just a rectangular hyperbola and there is nothing other than this. Okay, this is the ideal gas behavior. But similar thing if you do for real gases, because for real gas the equation is different. If this is P and this is V, so this kind of expression comes for ideal gas. Why? Because you know that PV equal to RT for 1 mole of ideal gas. So at a constant T, that means at constant temperature isotherm, your P into V is equal to just constant, which is just an equation for rectangular hyperbola. But for real gases, there you have the equation as P plus A by V squared into V minus B equal to RT. This is for 1 mole of gas, and this is a real gas which is non-ideal, and this equation is called the van der Waals gas equation for real gases. Okay, so by this equation you see that there is a cubic dependence on the volume, because if you multiply these two terms there will be a V cube dependence. Okay, and that means whenever you have a cubic dependence like that, so in that expression you will get 3 roots as a value of V, right? So this is a cubic equation in V. That means it has 3 roots obviously. So the nature of the curve will now change. It will not be a simple rectangular hyperbola, because it will now take a shape like this. Okay, so if you now draw a line here, which is a constant pressure line, along this line the volume is varying but pressure is fixed, and here the where it cut the curve are the intersection points, this and this. So you see that there are 3 points where it cuts the curve, and these are the 3 roots that I was talking about, that is coming from the cubic dependence of V cube in that real gas expression. So now if you, this is at a constant temperature, let's say T1. Now if you say increase your temperature, so the next curves will be looking something like, the set of curves will be looking like yeah, so we maybe first draw a line for our reference. The line, dotted line, will be going from the peak and deep of these curves, and based on this the next line will be, let's say this is our next straight line. This one, and then sorry, I think there is a, so let me draw it first and then, yeah, so this will be like this. Again, if you draw a last straight line, you get 3 cuts or 3 intersection points or 3 roots. So basically the dotted line will not be like this. We'll draw the dotted line accordingly as per the peaks and deeps positions. And now the next curve will be like this. So this is at T2, this is at T3, so the temperature is increasing, and finally as you increase the temperature even more, at one point you will get, so this maybe we should extend this, at one point you will see there is, the curvature is almost gone. Okay, so till this point also you had a curvature, this and these were the roots. Here also they have a slight curvature, this and this were the roots, but here there is no curvature. So let us try to join this first root by a dotted line for all these curves, and also the second root, the last root. So what line do you get is some kind of a, this kind of a line. This is just for a line of line guide to the eye, and then you can also connect the dips here by a line like this, and the peaks here also by a line like this. So this is for further increasing temperature. So for T3, then T4, then T5. So temperature is increasing here, right? But this is the point where we are interested about, is the critical point. Why this critical point? Because you see the behavior that it was following till now, the PV behavior is gone from here, it has become flat here. So this is your critical point, where the temperature here for this particular case is equal to Tc. This is the critical point temperature. So for here, if you mark it as T5, this will be nothing but Tc, which is the critical temperature. And the pressure and the volume corresponding to this point, so here the pressure is P equal to Pc, and let us call the volume on this point as Vc. So this is the critical point value, Pc comma Vc. Okay, so basically this is for real van der Waals gas behavior. Okay, now you can clearly see that what is the critical point. At the critical point, the slope is first of all 0, because this is almost a horizontal line at this point, right? So the tangential line, if you draw, the slope will give you a 0 slope. So at critical point, the slope of the P versus V curve is 0. That is one thing seen from the graph. And the other thing that is seen here is that the curvature is changing right from the critical point. Initially it was concave upwards, and then from this critical point, after this critical point, the curvature has changed to concave downwards. right? So initially it was concave up, then it became concave down. So mathematically speaking, from the critical point value, the curvature of the PV curve also changes from one to other. So basically here you know that the curvature formula is basically the double derivative of that expression, and slope is nothing but dp dv, because if it is a PV curve, the slope of that curve will be dp dv, dp by dv. Similar to just like you draw x versus y versus x plot, so the slope of the curve will be just dy dx, right? So similarly here dp by dv is the slope of this PV curve, and the curvature is the double derivative of the slope, so it will be d2p by dv2. So the main conditions now we are familiar with is that you have to use the two conditions, that at critical point, which is defined by TC, PC and VC. Let me also write this, the critical point parameters. At critical point, slope of PV curve is equal to dp by dv at constant temperature is 0, where the constant temperature is T equal to Tc. And the curvature changes at critical point, let us call it C, or critical point, let us call it C. So the curvature also changes at critical point, and the curvature of changes means C is also the inflection point, right? This is the point where the mathematically the curvature of the curve changes, so that is called our inflection point. And the idea of inflection point is that at the inflection point, the double derivative of this P versus V curve, d2p by dv2 is also 0. This is also at T equal to Tc constant temperature. Now this is, let's say, condition number 1, and this is, let's say, condition number 2. Now you just have to use these two conditions. So from 1, dp dv, first of all let us calculate from the expression. So sorry, okay, I may not have done it correctly. Let me try once. Okay. Right. So this was our van der Waals equation, right? So we choose the marker. This was our van der Waals equation. So from here we can calculate our dp dv, because you can just let us choose this to write in terms of p only on the left hand side. So this is rt by p minus b minus a by p squared. So your dp by dv is just rt minus rt. So you just have to take the derivative with respect to v, minus rt by p minus b squared plus 2a by v cube, which is nothing but 0 as per the condition number 1. So from here you also get that 2a by vc cube is equal to rtc by vc minus b whole square. Because this is, let us call it as equation number 3, because here you know that at critical point v equal to vc and t equal to tc. So we have just substituted these values. Okay. Now once you have this, so from here you have to take a double derivative for condition number 2, which is d2p by dv2. First let us calculate that. So this is plus 2rt, again take a derivative, p minus b whole cube minus 6a by v to the power 4, this is equal to 0. So this is simply 6a by, so we'll cancel this 2 and 6 as 3a by p to the power 4 equal to rt by p minus b whole cube. Now you know that here v equal to vc, so replace it by vc and t by tc, right? So this is your equation number 4 in this case. Now from 3 and 4 you can simplify this and you can get a solution from 3 and 4, that you do 4 by 3. Then you have 3a by vc to the power 4 into vc to the power 3 by 2a. is equal to RTC by PC minus B whole cube into PC minus B whole square by RTC. PC minus B whole square by RTC. So these and these cancels out. A and A cancels out. So this is 3 by 2 times Vc is equal to 1 by Vc minus B. So this is just 3Vc minus 3B is equal to 2Vc. So from here, by solving this, you get Vc equal to 3B. So our critical volume is already obtained as 3B. Now once you have this, you can use this one and you can put the value of Vc as 3B. So this is 3 to the power 3 is 27, B cube is equal to RTC by 3B minus B is 2B, 2B squared is 4B squared. So this is TC is equal to this B square and B cube gives you B. So this is 8A by 27 RB. Right, so TC is also obtained. Now once you have TC and VC, you can get PC, which is like PC equal to, you have to use the main expression. This is RT by V minus B minus A by V square. So this is now RTC by VC minus B minus A by VC squared. So this is just R into 8A by 27 RB divided by 3B minus B is 2B minus A by 3B square is 9B square. So this is R and R cancels out. So this is 8A by 27B into this 2B is, right? So this is 4 minus A by 9B square. So this is 4A by 27B squared minus A by 9B squared. So this is 27B squared 4A minus 3A, which is like 9 by A by 27B squared. So this is your PC. So now you have all the three critical parameter values PC, VC and TC. So you can easily get the critical coefficient equal to RTC by PC VC, which is like R into 8A by 27 RB into 1 by 3B is 1 by VC, then 1 by PC is just simply 27B squared by A. So you have A and A cancelling out, 27 and 27 cancelling out, R and R cancelling out. So you have 8 by 3, this B square and B squared, this B squared cancelling out. So 8 by 3, which is like almost like 2.67. So this is the critical coefficient value for real gas. So eta C, real van der Waals gas, which follows this particular equation of van der Waals gas. If you change the gas equation, then obviously this constant value will also differ, because then the PC, VC and TC value will differ. So sometimes there are problems in the context of this, where instead of van der Waals equation, they will mention to you a particular different equation connecting P, V and T, and you have to by the same way solve for the slope and then equate it to 0, then solve for the curvature, double derivative and equate it to 0, and in the similar manner you have to use a different equation altogether and have to find out what is PC, VC and TC, and finally by taking the ratio you will get the critical coefficient eta C. But now for van der Waals gas I am saying, because it is following van der Waals equation. For this particular equation, the eta C value is 8 by 3, which is nearly equal to 2.67, which is greater than 1, you can see. Whereas for ideal gas, in all cases, for ideal gas, the critical coefficient value is fixed at 1. So, because this van der Waals gas value of critical coefficient is greater than 1, so basically it is deviated from ideal gas behavior. Okay. So, this eta C is basically a measure of how much the departure of the real gas is from the proper ideality of the gas. Okay. Right, ideal gas behavior. So this is also done. So this was a little something extra, but I thought it will be helpful, because even if you have been given a different gas equation, you can then calculate how to get the ratio of RTC by PCVC. Okay, so now question number 7 is about, for a solid, the Debye temperature theta D is 500 Kelvin, then calculate its specific heat at a temperature of 75 Kelvin, assuming low temperature behavior. Okay, so your theta D value is given to you, then you have to calculate CV, temperature is mentioned as 75 Kelvin, and also there is said that you have to assume low temperature behavior. That means you have to use the low temperature limit value of Debye theory of specific heat. Then you have to calculate for CV. Okay, so let us do that. Question number 7, right? Yeah. So for question number 7, your Debye temperature is given as theta D is equal to 500 Kelvin, and you have to calculate for CV. Temperature is given as 75 Kelvin. So now it is particularly mentioned that you have to use the low temperature limit, even if the temperature is 75 Kelvin, which is low obviously, but in the question they have mentioned explicitly that you have to use a low temperature limit of Debye's specific heat formula, which is CV is equal to, I have used this formula earlier for probably question number 1, so you'll use the same formula, that it is 12 pi to the power 4 R by 5 into T by theta D whole cube. Remember that this is only for low temperature limit, okay? So this is valid here. Now just put the explicit values for each of these terms. This is 12 pi to the power 4 into this R value for SI unit. If you if you try to calculate, that means in joule units, if you see, then this is 8.314 in SI units, divided by 5 into T75 divided by theta D is again 500, then whole cube. So if you calculate this, you will get 6.56 joule per mole Kelvin. So this is our answer. So let us go back. Question number 7 is that yeah, so this is the correct answer. Correct answer is C, right? This is matching. Now question number 8 is about, for a certain metal, the velocity of longitudinal waves is half the velocity of transverse wave. Then what is the Debye frequency if the number of atoms per meter cube is 10 to the power 29 and the velocity of the transverse wave is 3 km per second. Now here, if you remember that in the Debye theory of specific heat, Debye had modified the assumptions that Einstein had used for the original theory, using the quantum application or quantum theory for the specific heat calculation. So in this Debye's calculation, this idea of transverse and longitudinal waves came because in the lattice he had used the consideration of atomic vibrator or oscillation in a particular frequency. And in the context, if you can look up to that particular part of the lecture, you will find the formula for Debye frequency and how it is related to the velocity of longitudinal wave and transverse wave. So I will be directly using that formula, and using the necessary parameter values that are given in the question, we will solve this, okay? So here you need to know the exact formula to solve this. So this is question number 8. And in the question it is mentioned that the number density, the number per unit volume for this particular case is 10 to the power 29 per meter cube. So this is in SI unit, meter cube, right? And the velocity of the transverse wave, so T means, T subscript means, here I am meaning to say transverse wave. So C subscript T is the velocity of transverse wave, and that is equal to 3 into 10 cube meter per second. This is given. And for longitudinal wave, the velocity CL, which is half of the transverse wave velocity, that is also mentioned in the question, and here the L subscript means longitudinal, right? And you have to calculate what is the Debye frequency, nu d. So the connecting formula here is basically, the primary thing for this solution is nu d is equal to 9 times Na divided by 4 pi V 1 by CL cube plus 2 by CT cube to the power of 1/3. This is for 1 mole. That is why you have this Avogadro's number. So you know that Na by V is equal to then, here this is for 1 mole. So if instead of 1 mole you have in general expression, so then Na will be replaced by N, right? General number of molecules. Replace Na by N as total number of molecules in general and not specified for only 1 mole. So we'll do that. We'll replace this. If you are not considering only 1 mole, so for a general idea it will be N, right? So, and we have this information about N by V, which is small n, number density. So here this N by V we can take it together and make it N by V as the total N. So other values we know, so we'll put those values. So 9 into N by V is small n, which is like 10 to the power of 29 divided by 4 pi. Now this V is up, so there is no role of V here. So this is then 1 by CL cube, right? So first of all, CL was half of CT. So we'll replace that 1 by CL is then 2 by CT. So then 1 by CL cube is just 8 by CT cube, plus here it is 2 by CT cube to the power of 1/3. And then this is just 9 into 10 to the power of 29 divided by 4 pi divided by CT cube, this into 10. So this is to the power of 1/3. Now this is 9 into 10 to the power of 29 divided by 4 pi. CT cube, you know the value of CT as 3 into 10 to the power 3, right? So this will be 4 pi into 10, the CT cube will come up. So this is 3 into 10 cube and to the power of 1/3. So if you calculate this, you will get a value close to 5.78 into 10 to the power of 12 Hz. Okay. Right. So this is our answer that we have obtained. Now we can match that answer with any of the options that is given. So the answer is like 5.78 into 10 to the power 12. So this is option number A. So this is right. Then question number 9 is about, at low temperature the specific heat of solids can be expressed as which one of these options. So this is pretty straightforward, so I will just write it down by the side of this. This we know from the idea of specific heat already, that your CV is a combination of two terms, which is like AT plus B T cube, where A and B are just constants. Okay, most of the times more standard expression will be like gamma T plus beta T cube, because this gamma is the Sommerfeld constant and this beta is a constant coming from the phononic contribution. Okay, so the idea is that the low range specific heat, so the low temperature range specific heat especially behaves like this. In the high range it will saturate to follow the Dulong-Peretz behavior. In the middle range then there is some other numerically solved behavior, but mostly in the low temperature range there are two terms that dominate, which is the one is from the lattice vibration term, which is the phonon contribution. Lattice phonon, basically lattice vibrational waves are called phonons. So lattice vibration or phonon give rise to this T cube dependence, whereas the gamma T behavior, the linear T, is from free electron contribution. Okay, electronic contribution to specific heat. This is seen in metals. So our answer will be AT plus BT, which is option number C, which is correct. Now the last question is that the dimension of B in van der Waals gas equation is similar to that of which one of these options? Pressure, temperature, volume and B is dimensionless. So this I have already emphasized earlier. I will again tell you that B is something that is a correction term to the volume in the van der Waals gas equation for real gases. So obviously the first, let us take the answer. This is the volume. So this is the correct answer. So B is basically related to volume, because B itself has a particular formal name called co-volume. So why it is co-volume? Because I told you that in the van der Waals expression is come in the term P plus n square A by V squared. So this A, sorry, n square A. So this A, if you have the question like what is the dimension of A in van der Waals gas equation similar to that of, then you will have to choose the option as pressure, because A is in the term of pressure in the equation, but B is in the V minus B part, right? So it is already related to volume. So B is related to volume. Okay, it has the dimension of volume, and A is related to pressure. So I will not say it has the dimension of pressure, because ultimately there are other terms also, P plus n square A by V square also. So if you are considering the dimension of A, then you will also have to consider the V dimension also here. But basically A is mostly related to the pressure term, because it comes from taking into account the finite interaction that is happening in between the gas molecules, which was avoided or neglected in ideal gas behavior. And this B is coming as a volume correction term, because in ideal gas we used to assume that the gas molecules are occupying no volume, they are like point masses. But in real gases we are considering that the gas molecules do have a finite value, no matter how small that is, and that will actually change the effective volume for the whole system, for the other molecules to move freely about, and therefore you have a reduction in the net effective volume as V minus B. So B has the exact dimension of volume, because this is just V and B, there are no other terms present. So this is pretty much simplified. So with this we have finished the earlier assignments, which I think most of the questions are common to the current assignment given to you. There are some questions which are new, or which are not discussed in the question types that I have just now discussed for the earlier case. So that I will cover, so that you have no problems in attempting it in the assignment, in the current week's assignment. So here, like say question number 1 is something that is a new question, because here they are asking you about the Einstein temperature or Einstein's equation. You have to formula of specific heat you have to use, rather the Debye formula that you have used to solve multiple problems in the earlier assignment. Okay, so like this question I'd like to solve here for you, that whenever they have mentioned you the Einstein temperature, that means similar to theta D, the Debye temperature, you mark a theta E, which is like your Einstein temperature. So you can find this expression and find this idea from the topic Einstein's theory of specific heat in the specific heat chapter. So this is Einstein's temperature, which is given as theta is at 70 Kelvin. Then you have to compute CV at a temperature of 50 Kelvin. So it is the exact same question if you see in the earlier assignment, but instead of using Debye formula, they have asked you to use the Einstein's formula. So this is the exact same question. I think the question was later on. Yeah. No, so not exact same, like the values are different, but obviously the information about the question is exactly the same. So we'll proceed with this question, that at T equal to 50 Kelvin you have to calculate what is CVT, and R value is given. So first of all you have to use the Einstein's formula of specific heat. So Einstein's formula of specific heat. Okay, so because by 50 Kelvin you assume that you are in the low temperature limit. Again, just like Debye theory, Einstein's formula also have a high and low temperature limit. At high temperature limit it behaves like a classical Dulong-Petit's law expression, but for low temperature limit its behavior is different, and that is simplified to have a exponential dependence. So I will just write down the expression that in the low temperature limit CVT is equal to 3 times R into theta E Einstein temperature by T whole squared into e to the power of theta E by T divided by e to the power of theta E by T minus 1 whole squared. Okay, right. So this is the expression that you have to use. Now you just have to take the ratio of theta E by T. So here our case theta E by T is just I think 70 by 50, right? So this is 70 by 50, which is like 7 by 5, and you just put this in the expressions here, and you use the value of R in the question is 8.32 joule per mole Kelvin. So this is an SI. So it is 8.32 into 7 by 5 whole squared. Now the exponential term you have to calculate by the calculator carefully. e to the power 7 by 5 minus 1 whole square. So if you calculate this, you will get a value of, I think, some 21 something you will get. So let us see what is the option close to that. So okay, this is 21.23. So there is another option in 20s order. So let me calculate this explicitly so that we can know the exact answer. So this is 3 into 8.32 into 7 by 5 whole squared into e to the power of 7 by 5 divided by e to the power of 7 by 5 minus 1 whole squared. So we are getting 21.25. Okay, so this is the 21.25 SI unit. So this is closer to 21.23. So the correct answer will be option number A in SI unit. So this is joule per mole Kelvin. Okay, now this question is similar to, we have already calculated this in the last assignment. Now find the temperature at which Einstein frequency. This you can try and solve by yourself, because as I said, this is just the same formula, same notation, same way of calculating. Just instead of divide, they are telling you to calculate the Einstein's frequency. But again you have to match the energy scales, that H nu equal to kBT, match the frequency corresponding energy scale with the temperature corresponding thermal energy, and you will get the value of the Einstein temperature. So here it will be like kBT is equal to H times nu E, where nu E is the Einstein's frequency, and kB value you know, H value you know. So from here you will get T. So you can calculate it and take it by yourself. Then this question is already common, we have already done this. Okay, so I'll skip that. And then question number 5 for helium, critical volume is this. Then calculate the molecular diameter of helium. This also we have done. So we'll skip that. Then question number 6 is about 3 A and B values are given, pressure. This is also done. For a solid, the Debye temperature is at 500 Kelvin and specific heat. This is also common to question number 1 in earlier assignment. Done. Then question number 8. Okay, so this is also common. Rather, only I think the values are a bit different. So the calculation will give you a different value, slightly different value, but the total formula and nature and the statement of the problem is just the same. So I'll leave it to you to solve and get the exact value. Then this question number 8 is that so this question number 8 is repeated here. So this is done already. Now question number 9 is something that is new, that is not done in the earlier assignment. So that I'll solve for you, and let us first check question number 10 before that, if you have to discuss that about something about that question. So this is again, mass is given, for volume is given, pressure is given. So m given, volume given, pressure given. Find the temperature assuming it is real gas. So A and B are given. So basically you have to use the Van der Waals real gas equation. So this is very obvious, right? Because all the information is given to you except for temperature. So then you have to use P plus N square A by V square V minus NB equal to nRT. So the T will be calculated from here. N is the number of moles which you have to calculate from the mass. Divide the mass by the molar weight of helium and you will get the number of moles N. Okay, and A and B value are provided to you. V and P is also provided to you, and R is a universal constant, that value you know. So from there, just taking care of the units carefully, you can get the temperature value. So you can solve it by yourself. So we are more concerned about question number 9, which is sort of new. So let us read that question. So a primitive cubic crystal has lattice parameter of 0.3 nanometer and Debye temperature of 100 Kelvin. Then estimate the speed of sound inside the crystal in meter per second. So this kind of problems where the speed of sound is involved, so there is a particular formula for such cases that you have to use to calculate Debye frequency, which we'll use. But for that, so there are basically, it is obviously mentioning to you that this is about primitive cubic crystal. So that means it is a 3D sample, right? 3D means it is a crystal, so obviously it is in 3 dimension. And the lattice parameter, which is we call as A is given as 0.3 into 10 to the power of minus 9 meter. And the device temperature theta d is given. So the speed of sound, we call it as V subscript S, speed of sound. That is what you have to calculate. So as I said, that I will tell you a general formula for solving this kind of a problem. So even if instead of a 3D primitive crystal you are given a 2D structure, then also by using that general formula you can solve it. So this is the current assignment, problem number 9. Okay, so this is about the formula connecting speed of sound and d by temperature or d by frequency. Okay, so first idea is that there is a dispersion relation, right? So dispersion relation you can write is like omega is equal to Vs times K. So this is a generic dispersion relation that you know, where this is in the crystal or in the system, whatever that you are given. This is the sound speed Vs, and K is just the you know that the K is the inverse of the lattice, like it is a lattice, what do I say, lattice parameters inverse. Basically I am forgetting the exact terminology for this, but you probably understand that this is just same K as equal to h square k square by twice m. So this is that K, wave vector. Yeah, so basically K is a wave vector in the lattice, and omega is your this frequency, angular frequency, which is like 2 pi nu, where nu is the actual frequency and omega is the product of 2 pi nu, which is the angular frequency. Now this omega is equal to Vs into mod of K. So you know that there can be 3-dimensional approaches in this problem. Depending on the dimension, the formula will be different. So I'll write down the dimension one by one and then again a generalized version, and then finally apply it for 3-dimension and get our answer. So for 1-dimension case, so for a 1D monoatomic chain system, there you know that if your lattice parameter is A, then your K is simply pi by A, right? Because A is your lattice parameter. So then omega is equal to Vs. So here omega is equal to omega d, which is the d by angular frequency, and this is equal to Vs into pi by A. So now you take the total length as L. So your L will be like n times A, where n is the total number of cis atoms present in that, and A is the distance between each of these atoms. Or it is in other words lattice parameter. So if it is a chain like this, okay, so this is in 1 dimension, so then there are n such circles or n such atoms. Okay, so this is 1 2 dot dot dot, this is n such atoms you will get, and individual distance is A for all of them. So the total length, let's say from here, let's say from starting from 1 to n, whatever the n is, so we'll get whatever the finishing point is where the n is sitting. Okay, 1 2 3 4, and n is maybe sitting here. So then your total length of this line will be n times A, because individual distance is A and there are n such things, so L equal to NA. Okay, so then your A equal to just L by N. So this is just Vs into pi into N by L, right? So this we can call as Vs by lambda equal to omega d. This is for 1D, where lambda is your n by L, which is your linear number density. That means number of molecules per length, because it is in 1D, so there is lambda. Okay. Now for 2D, if you talk about the same thing in 2D, which is like 2D monoatomic square lattice. So this is not lattice, but this is in 2D. So then the formula is omega d square dy frequency squared equal to Va squared into 4 pi by A squared, right? So then you get, so this A is again your lattice parameter, so A square has a equivalent area dimension. If you take a unit cell each of side A, then the area of that cell will be A squared, right? So then your this thing will be 4 pi by A squared. So this you can write down as 4 pi into n by A into Va squared. So similarly, like you had L equal to NA, so that you had to write A equal to L by N, or then 1 by A had become N by L, right? So similarly here, your total area equal to A equal to N times A squared. So this is the individual each unit cell area A squared, and A is the total area. So for all N atoms, so A squared is like A by N, or 1 by A squared is N by A, right? So this is 4 pi Va squared sigma is equal to omega d squared. So now sigma is just N by A, which is the number density, also called surface number density, because it is in 2D. It is the number of molecules in area. So this is called the surface number density. Okay. Similarly for 3D, you consider a 3D, which is in our case in the question given 3D monoatomic primitive cubic crystal. Why it is called primitive? Cubic because it has a cubic size, all the sides have same value A. And primitive is also because it is a simple standard kind of an unit cell of that crystal, where the each of the side length is A, right? So the unit cell volume will be, for each side A, unit cell volume is A cube for the cube, right? For a cubic crystal. So then your N times A cube is equal to your total volume, number of molecules into each number of unit cell into each unit cell volume equal to your total volume. So your A cube is equal to just V by N. So for this 3D case, your omega d dy frequency cube will be like Vs cube into 6 pi squared by A cube. So this is like 6 pi squared. A cube is just V by N, so 1 by A cube is N by V to Vs cube. So this is like 6 pi square into rho Vs cube is equal to omega d cube. So here rho is equal to N by V, which is like volume number density. It is in 3D. It is number density in 3D, because this is the number of molecules per unit volume. Now in the question, if you remember that they have explicitly mentioned the primitive cubic crystal mentioned. So basically it is a 3D case where you have to take the formula here to know the connection between this speed of light and the Debye frequency. Okay, Debye angular frequency. So here your omega d is equal to, here it will be also we can write down a general expression, as I was saying, that apart from just talking about only 1D, 2D or 3D, so there is also a general expression combining all these dimensions, that is equal to Debye frequency omega d to the power of n equal to e to the power of n pi to the power of n by 2 into gamma 1 plus n by 2 n by n to the power of n, Vs to the power of n. So here everything is in terms of n. Now you have to just put the value of n equal to, maybe cross check by putting the value of 1, and you will get the one dimensional case. You will get back to the one dimensional case. Let us put n equal to 1. So then omega d to the power n is omega d to the power n is 2, pi to the power n by 2 is 1, gamma 1 plus half, okay, n by L to the power 1 into Vs to the power 1. So this is just 2 pi lambda Vs, gamma n plus 1 equal to n gamma n. So this is half gamma half. So 2 pi lambda Vs into root over 2 root over pi by 2. So what are we getting here? So we should have obtained 4 pi by a squared, or 4 pi Vs squared, sorry, 4 pi, no, not 4 pi, Vs pi lambda. Uh, 1 plus half, n plus half, gamma space. So pi to the power n by 2 is just pi to the power, sorry, pi to the power n by 2 is also pi to the power half, right? So this is half. So this is 2 lambda 2 pi to the power of half, root over pi. Now lambda, this is lambda, this is Vs, and this is half gamma half. This is equal to 2 lambda Vs root over pi into root over pi by 2. So this 2 and 2 cancels out. This is lambda Vs into pi. So this is omega d. So let us check. Yeah, this was Vs pi lambda. So this and this matches. So basically this is the general expression that you can use whenever a problem like this is given to you, be it 1D, 2D or 3D. Now for us, for our question number 9, they have asked for a 3D picture, because they have used a primitive cubic crystal. Okay, so from there you have omega d is equal to lambda Vs pi, or what expression do they have about is that no, this is for 1D. So basically we have to use for 3D. So 3D is omega d cube equal to Vs cube 6 pi squared by a cube. So omega d cube equal to 6 pi squared Vs cube into 6 pi squared by a cube. So Vs cube. Okay. So then omega d is like Vs into 1 by a, then 6 pi squared to the power 1/3. Okay. So then I use the values of the terms given. So in the question it is given that your, what is that? Question number 9. Right, so question number 9 is your Vs you have to calculate. A is 0.3 nanometer and temperature Dy is 100 Kelvin. 100 Kelvin, 0.3 nanometer, you have to calculate Vs. So this, from this 100 Kelvin, you can equate always the thermal energy kBT theta d is equal to H nu d, right? So from here you will get, because you know all the other terms, you will get d by frequency nu d. And then by multiplying it by 2 omega, you will get the 2 pi, you will get the angular d by frequency omega d. So from there you can substitute the value of omega d here. Now the Vs value you have to calculate. So Vs equal to omega d into A into 6 pi square to the power 1/3. and the value of omega d is known from here. Obviously, value of a is given in the question, that it is 0.3 into 10 to the power of minus 9 meter, and these are all the known terms. So from here you will solve this and get p is equal to, I think it came as 1006.50 something. Let me check. So because I did it roughly, I did not take out the exact solution, but you can check out the exact solution from the question options given to you, and you should also do the solution by yourself using your calculator. So I got something like this one, 1006.50. So this is closest to 1007.19, and ours was this. So with this we are done with this week's assignments. Hopefully this will help you to solve this assignments problems that is given to you this week. And if you have any doubt, please let me know. We can discuss it in the next class. Okay.